Hello, everyone. So Bernardo and I will be talking about hacking bootloaders or creating a bootkit, and our talk is called "I boot when you boot." So yeah, I get you get the pun. So we first will begin with the introduction and what we do, who we are. Then we're going to talk about malware that already exists that runs on embedded devices. Then we're going to see how an embedded device boots. Then we're going to have a look at gaining persistence on embedded devices. Then we're going to talk about writing a bootkit and then how you can detect the bootkit and how you can mitigate risks that are involved here. So my name is Vincent. I work at the KPN Red team. I'm a moderator for New Amsterdam. So, if you want to talk someday, just let us know. I think Bipin is around here as well. It's right there. You can, ping us, send some slides, and you can do a talk. I like Linux. I like low-level stuff. And since we're giving a talk about bootkits, I might not go to the US anytime soon. And I live in Amsterdam.
So my name is Bernardo. I'm Brazilian. I'm also working at the KPN Red team. I play CTF with the Goonies. It's a Brazilian CTF team. And I'm very good at breaking routers. So let's start. So malware targeting embedded devices. Spoiler alert, this is not something new. So there are lots of malware already targeting embedded devices. So the CIA cherry blossom on the leaked documents from WikiLeaks, they all describe it how they're creating backdoored firmwares and that we can flash on home routers. But there's also known botnets like Mirai, so targeting embedded devices using weak passwords, but also, Flasher.a, which was basically a DDWRT modified firmware. So there are lots of kinds of malware targeting embedded devices. Some of them don't care about persistence. For example, Mirai. Mirai is just infecting a device and just start scanning the internet. And some malware like the one from CIA's, like the Flasher.a, they have some kind of persistence, but they don't care about the bootloader. They just flashing a new firmware. So
yeah, the boot process of an embedded device is slightly different of your everyday x86 device. So the NAND, or the NOR, in this case, the NOR flash is hard-coded inside the CPU boot code. So the moment you turn on the CPU, it boots to the flash, and on the flash it goes to the bootloader. The bootloader initializes the hardware, and then it jumps to the firmware that's gonna decompress the LZMA, because the kernel is usually compressed because it saves space. So it on LZMAs the kernel into RAM, and then it jumps to the first instruction of the kernel, and then from there on the kernel mounts the file system and then kicks off init, and there you go, your embedded device is booted. And you can see the typical boot process over there: bootloader, firmware, on LZMA into RAM, and then you're basically done.
So persistence, why having a persistence at a bootloader level, why is it interesting? It's because when you have a firmware upgrade, you go to the D-Link website, you download the firmware. When you flash your firmware, it's not changing the bootloader partition. It's just changing the firmware and all the other partitions, but it doesn't care about bootloaders, because reflashing bootloaders is a sensitive operation. If you do something wrong, you break your device and you need to open and manually reflash the SPI chip.
We had to do this a lot.
Yes.
Even when we were preparing our demos, yesterday, I bricked the device. It's
And it's also very interesting because you bypass lots of security features from the operating system. So all those UEFI bootkits on Windows and all those sort of things, and it's very difficult for you to detect. But, so just like NSA, I'm also really good at breaking routers. So there's this document on the Snowden documents. So that said, Snowden basically said that NSA tried to reflash a firmware from a Syrian router, and it kind of broke the internet for the whole country for a couple of hours. So it's a very sensitive operation. It's very easy for you to mess up, and it's not if you create a bootkit or a bootkit for one device, it doesn't mean it's going to work for other devices, other similar devices. So it's very particular to SOCs. It's very it's something that you need to work a lot. And yeah. So no. No.
So yeah, persistence can be gained in various ways. One of them is by modifying the init or the init RD scripts. You can also make a loadable kernel module that loads like after the kernel loads the file system modules. You can modify UFI or BIOS code. You can also modify the code in the MBR and the VBR.
And also, again, spoiler alert, bootkits, they are not new. So nowadays there are like ransomwares, like targeting MBR. So they're just putting like some message there, and they will only unlock after you pay stuff. But so two interesting bootkits here is like the old boot, Android bootkit. So some people said that was either like compromising devices physically or some like firmware update. They don't know exactly, but it's a bootkit targeting Android devices. So if you just like refresh your firmware, it's also like not changing the bootloader partition. So it's something like very difficult for you to fix. And also the hacking team, they had like a commercial UFI bootkit, but they're more like an implant. So if some motherboards, like some notebooks, they had like, they wouldn't protect that UEFI area. So sometimes you could exploit that to rewrite that. But most of the time it's by opening the device physically and refreshing the SPI, the BIOS or the UEFI. So there's like no malware, and they just like infect your computer the normal way, just like phishing, drive-by downloads, and they use a bootkit for maintaining persistence. So the bootkit we created, it's based on U-boot, which is like a bootloader for embedded devices. It works for lots of ARM devices, also MIPS devices. It's open source, we will explain in a bit. But in order for us to change the device, we don't need the physical access. We just need a root access on the device, and we're going to explain how it works. So Linux devices, they treat the flash partition as a memory technology device, MTD. And it's not exactly like char blocks or, block file systems that you're used to on Linux. They are just like a raw flash memory. And there's not like a partition is not stored on like each partition. Before starting each partition, there's nothing like a partition table. So the kernel, it's listed on the kernel where the partition begins and where the partition ends. So on this case, you can see like the U-boot partition, also like the actual firmware, like an ART partition. And the bad thing for us when we were like started testing this, it's like the bootloader partition is always mounted as read-only. Like, not always, but most of the time. So if we get a root shell on the device, we need to DD our bootkit into the device, but that like partition is read-only. So how can we do? How can we fix that? There's like these two kernel module called mtd-rw, so which is basically a Linux kernel module. So I can just in Smod load that Linux kernel module, and that would change the partition flags from read-only to read and write. So this is good for us because now from a root shell, we can change that partition to something else. So this is like the code of the Linux kernel module, but it's just simply changing the flags. And this is really good because now we don't need shell. We don't need physical access. We just need the shell, and we can just like DD. And one thing that's important to mention, like if I have two similar devices, the bootloader, the U-boot partition is not going to be exactly the same because there are like variable areas like serial, like MAC address. They're kind of different. So what we can do is we can just DD the offsets related to the U-boot bootloader, and we can just ignore the serial and just copy and that and just skip it.
So U-boot is an open source bootloader. So you could just download it from the internet. It's GPL source code, so GPL v2 license, which means that any vendor using U-boot has to provide you with the source code. So writing a bootkit like this becomes a lot easier than writing a custom bootkit. And we used in this case U-boot mod, which was an open source project from Pepe 2000, which is awesome programmer.
So why U-boot? There's this website called Wikidev. It describes lots of information about routers, embedded devices, cameras, and all those stuff. So U-boot is the most used bootloader on the website. So the second most used is CFE, which stands for Common Firmware Environment. It's proprietary. It's from Broadcom. So it's also like open source, but it's not as easy to modify as U-Boot, and it's not as used as much as U-Boot. So that's why we chose it.
So because we were planning on breaking the device like a lot, we had to make some preparations. We have a great guy in our team, his name is Frank, and he can solder everything, like literally everything. So we desoldered the SPI flash where the firmware and the bootloader is on. And he connected like the small pins that are connected to the SPI. He hooked them up to some wires. And then we used our, the tool we use for flashing SPI chips. We just hooked it up directly. So when we wanted to boot the firmware, we just put it in the thing. And the moment we bricked it, we just put that thing in our hardware flasher and restored it back to how it was. This saved us a lot of time. So U-Boot has some interesting functions. One is printenv. It prints environment variables. It has TFTP boot, which allows you to boot images from TFTP. It has an env stop string, which can be used to protect the bootloader menu from people who don't know the stop string. It's not a password, it's a stop string. And there's also a boot CMD, and the boot CMD is the command the bootloader will execute once the device has booted. And ping is like ICMP ping, so you can see if hosts are alive and do some things on a network. So you can also have scripts, and the scripts look a lot like the bash scripting language. Here's like a dual boot example. We will ping a hard-coded server IP, which is in the environment variables. And then if it's alive, we do a TFTP boot to the load address of a backdoor image. And once it's done, we will boot it. And otherwise, we will boot the hard-coded address that is from the normal firmware. So the printenv function prints environment variables, and the environment variables are all stored in a null byte separated list. So there's like 2 loops going over the null byte and reading the environment variables. And the function that prints the environment variables is inside the nvedit.c command. And we made some changes to it. We basically made 2 functions. Like one function is called getMatch, and the other one finds a variable. So we made a list also of null separated environment variables that we want to backdoor. And then the moment you want to print an environment variable, it like iterates through our list. And if it sees like, I'm not going to print boot CMD, then it's just going to print our own custom boot args or our own custom boot CMD. Another interesting function is the bootcmd function. Like the first command executed by the bootloader is bootcmd. So once everything is initialized, it will just execute bootcmd and boots a specific memory address. And we overwrote that in source, as you can see here. It's usually an environment variable, but we decided to skip that part and just hard code it in the source. So it will always use this as a bootcmd. Now we have a demo where we are dual booting. No, you can hold it. Let me see if this works. Oh, no, that didn't work. What just happened?
Full screen not working. It goes on this full screen.
It goes on this one. So, let's see. Display. So what we're going to do now, we are going to boot. Where's the mouse? Where's the mouse? Can you hold this for a sec? Yeah. So, there it is. Where is it? Space. So
Mike. Mike.
First, So now it's like not alive because this is our TFTP server. It's not on yet, so you can't reach our hard-coded server IP. So the ping failed and is now currently booting the normal firmware.
It's interesting because this function we created, like we ping our server. If our server is not alive, we just boot the regular firmware. So it's like a kill switch. So if our server is alive, we can do stuff. So this is like he's checking the version of the kernel, which is like the regular one.
And now we enable the server. And the moment we can ping the server, it means that the bootloader can ping the server. And it will start downloading our customized kernel from our server. And you can do this in theory over the internet. We haven't tried that yet, but it should be possible. It's a GLI net. It's a very small router.
It's on his backpack, so we can show you.
Yeah, if you want to see it. So now we booted our custom kernel, and it's a newer version. We're currently building a custom kernel, but it is a little bit more tricky than we thought it would be.
So you actually backdoor the kernel, so the image, which loads?
So we're downloading, we're using TFTP to get a modified kernel, but like the actual file system is the same. Because we can just say like, the kernel is this one, different one, but like you do everything else just like you do regularly.
Yeah, so we can load a custom kernel, and the custom kernel can make changes to the file system, which is later mounted by the regular one.
So we can put like Linux kernel modules, put a CPIO, and like you just like extract and load that before mounting everything. So it's a different kernel, so we can do everything we want.
Using the bootloader, you have
exactly.
Exactly.
Yeah, and by having control of the kernel, we can load the existing file system and make changes to the normal file system. So we can be persistent, on a new next level. So yeah, U-boot has a password protection. When you will Google a U-boot password, the first thing that will come up is the env stop string we're using here. It is not a password protection, and it should not be used as a password protection, because you can just download the firmware, run strings on it, and you'll see the password. So never use it as a password. It's easy.
Lots of vendors use it as a password.
And you can also really easily bypass it by glitching, which we are going to show you right now, if I can get my mouse on the other screen. Right, so there we go. Yeah, so what we're doing now, we're going to wipe the device first. So what we did is we created the stop string, but we made some changes to the code that where if you press an incorrect key or you try an incorrect password, it will wipe the device. So you cannot use the device. So if you have like an incident response team that wants to take a look at our malware, yeah, we don't want that. So let me see. This really sucks. I'm going to do this. Put it here. What's happening, dude? It's too no stuff.
Yeah, the mouse is here.
Yeah, I know. So play this. Into the next video. Yeah. So, yeah. So now we're going to wipe the device. So first we're booting it in a regular way. And then we will reboot it and press the invalid key.
It's also important to mention that you only see all those information if you're connected to a serial. If you're using like a serial connector USB.
So now we're rebooting, we're trying to press the key and it says nah, and then wipe the device.
So, and we can just like DD, we can just like put zeros and we can do everything. So U-boot has a native erase command we can use, but we can also write zeros, use like write memory to the actual partition.
And we can even write to the variables that are, the clock speed. So we could even overclock the device and fry the device. So you can never use it. It's really great. So we hide from strings because I play some CTFs where you just run strings and you see the secret token. So we use a little trick, and the trick is to make a byte array. And then we use string copy to copy the byte array into the string. And then when you run strings on it, you won't see anything. And when you put it in this is like an x86 example of what's going to happen. It's going to move the individual bytes into a string and then compares the string. So you need to look a bit harder into the source code. But you can easily bypass this, which we are going to show you now. I'm going to put the video here again. Yeah. So we had some wires that were connected to the data out pin. So we load the bootloader into memory, and then the moment you want to load the kernel, you just short the data out pin, and then it will fall back to the bootloader. So you have access to the bootloader. That's what we're going to do right now. Like, whoop, and there you go, bypass the password protection. It's really easy.
So what can you as a defender do to like detect bootkits or to do stuff? So U-boot has this thing called reproducible builds, which means that I can compile U-boot and I can hard code a timestamp. And if like I compile today and someone compiles tomorrow, or if someone compiles using a different system, it's all like the data partition, the code partition is always going to have the same hash. So there's like this source date epoch variable, so you can already do that. So for example, Debian is using reproducible builds for all the packages, their DPKG. So you can actually check if the source code and everything is the actual one you downloaded. So it's something really useful.
So Debian was backdoored by the CIA once, and they were entirely compromised, and then they started to really pay attention to reproducible builds.
So there's also this project from Intel, I think, called ChipSec, and which is basically a framework where you can use to read the content from like BIOS, UEFI. It's not very focused on like U-boot and all those stuff, but yeah, we can always like write patches or, submits and pull requests and do stuff. And there's also this really interesting project called non-UEFI executables. So it's also from Intel, which is just like a GitHub repository with known UEFI images, and so you can just like hashes from all different vendors. So it's just like a big repository, so you can just query and look up and to make sure like you're running an actual like valid or known firmware, or if it's someone tampered or modified. And this is like the output from chipsec. So you can, for example, run it on a MacBook and check if someone tampered with the BIOS, or if someone like disabled the read-write flag, you know, so it's not read-only anymore. So you can do lots of stuff.
So basically, chipsec strips away the variables that are custom to your device and just looks at the code that the devices have in common. So when you place a backdoor, one of the common code segments would be different, and chipsec would detect that.
So there's this presentation from the Google security team. So very few companies nowadays, they're good enough to find, you know, hardware implants or modifications inside their firmware. So Google, I think it was during RugsCon in Australia. So they explained how they're like tackling, how they're dealing with that. And like they have this tool called Google Rapid Response, and they were explaining how they're integrating chipsec to their like incident response and like their agents. And also like why is it so difficult? So it's just like we explained on the U-boot case. You have a code area and you have like a variable area. If I'm just comparing hashes, it's not gonna match. So I need to be able to parse that, unpack, and like for every different vendors or things like that. So trusted computing is something like very important. So there's like this tweet. So, and Dino is basically saying like, if UEFI secure boot suddenly started booting unsigned images, how many companies, how many people would just like could find that? It's something very difficult. So inspecable systems, this is something like that we need nowadays. And this example here, so also leaked on the Snowden documents, showing that NSA was basically intercepting packets. This is like a Cisco device, and reflashing the firmware with a backdoored firmware. And then, you know, as soon as it arrives on the guy on the other side, they can collect data, they can like access that. So very few companies would know if the device that arrived there is the actual device that suppose that the vendor sent it. So some companies are starting to use secure boot. So there's this company called OpenMesh. Their devices is just like the device we showed here. They're quite similar. It's an AP, wireless repeaters and all those things. So they're using secure boot. So they're also using U-boot, and they have signed images. So the bootloader is signed using an RSA key. So the problem here is that the RSA key is inside the same firmware flash, so the same blob. So you have like all your data, and you have somewhere there where there's the signature. So if the signature doesn't match, if I'm trying to boot a modified bootloader, it would just don't boot. So what happens is because U-boot is GPL v2. Some guys, they just asked the source code, they code reviewed, and they found out that if you erase, so this is just like a series of DD commands. So if you just erase the signature from the flash, it's not going to check and it's going to bypass it. So yes, there's also a Stack Overflow on the U-boot TFTP boot. So on our case, we use TFTP boot to download an image from the internet, but there's also a Stack Overflow on that component. So you could just like download a really big image, like causing an overflow, and then you could just jump to the bootloader itself. Then you could do whatever you want.
Which is really hard, and you probably need a JTAG debugger, but it's, yeah, something really cool. And it's a feature, not a bug, apparently.
Yeah. So bypassing secure boot, there's like some talks from Riskur guys. It's really interesting, like using glitching and all those stuff. So we did like the poor man's glitching. It's just like a simple way, but you can always use like specialized hardware or different things to bypass secure boot. There's also this Aleph research. So it's really interesting. They have all kinds of bypass for mostly for mobile bootloaders like cell phones and all those things. And yes, the conclusion is that like secure boot is important. So we have to like start thinking about that. also for embedded devices, for small routers and those things. And we need to reduce firmware opacity, which means that transparency is important. So vendors nowadays, they worry too much about tamper-proofing. So there's all like smart cards and all those stuff. They don't want you to tamper with that. But they don't offer any good way for you to know if the hardware that you got there is the actual, like, legit hardware. So Intel ME, which if you guys like look about it, they had like this backdoor, and it's very difficult for the the actual CPU to know what it's doing or what it's doing, not doing.
And the ME controls parts of the CPU, so you could do basically anything. So it's really important that we develop tools and get hold of tools, create tools, and so we can have a look at our hardware and what runs on our hardware. Because if we don't know what's running on our hardware, how can we trust our software? Because the hardware eventually controls the system.
And people, older people here, I'm not sure if you had like all those old motherboards, and there was like this jumper that you had to actually use because it's a physical impediment. So the BIOS is read-only. If you remove it, then you can write it. So it's a simple thing. It's a physical impediment. So if you can have that, you have like a more secure. Suppose you want to update your like home router, you can just switch it or just remove a jumper. So it's simple things that people are not using anymore. So also we need also better documentation, reverse engineering scripts, and and we need like better parsers for bootloaders. It's something that we need to understand so we can respond accordingly. And
questions?
Questions.
Of course.
Yeah.
You get paid for questions or what?
So at the moment we have several billion IoT devices in the world, and that number is forecasted to grow rapidly. So the way that you're showing it in this presentation is at least that 50% that you can access, there's really easy ways to get around everything. So if the problem's only going to get bigger, how are we going to scale our solutions to that?
It's a really hard question. So it's going to get the smart guy over here.
Yeah, so I think it's interesting for us to show ways for you to attack devices so people would start like better protecting them. So I think, for example, there's no malware targeting bootkits nowadays. So I think why we found it's interesting for us to like give a talk about that, it's something like not that complex, but because it's so easy for you to hack an embedded device, like Mirai. Mirai doesn't care. So if it infects the device, it's gonna, someone turns off, it's within a couple of minutes, 2 minutes, 4 minutes, 5 minutes, it's gonna hack it again. So I think people should like start like showing proof of concepts, and trying to reach. Okay.
Yeah.
Yes. And yeah, basically, so I think we should like have POCs, proof of concepts, so like ways for you to attack the device, and so people can understand the threat. Yeah.
Thanks. So you connect the device using SPI, I believe you said.
Yes.
So the device is well documented. It's open source. But for a lot of the first phase of disassembling a device like this is like reconnaissance phase, right? Like right up in the kill chain. We're going to have a look at the chips that are on it. We're going to Google the chips. And the moment you find a data sheet, it explains everything to you.
So yeah, it's very easy for you. If you can just look the device, you can Google and find the data sheet. And it explains like this is the DI, this is the data in, this is data out, this is the ground. So you just connect it accordingly. And there's like flashers, there's like hardware flashers you can just plug and dump. Or if you have, for example, a Raspberry Pi or a BeagleBone Black, for example, they have all those connections for interfacing with SPI. So you just need to connect the correct wires, and you can just reflash it. So the way we did, I think I can show them the device. But what we did, we got the device, we desoldered the SPI flash, and we connected those wires. Okay, so it's not here. Yeah, we can show you. But yeah, so we desoldered it, and yeah, and then it's very easy for us to use a hardware or just like Raspberry Pi or anything like that.
And if the chip, you can't find anything on the chip, then you need to go with a logic analyzer or with the other thing. What's the thing called? No, yeah, but no, not the JTAG later, but then it's going to be a lot harder Yeah, that's. Yeah.
Just one question. You mentioned.
Wait.
So you mentioned that we have some. You are looking for some ways to protect and check like the hash, etc., of what we're putting. Do you know what kind of algorithms are being used? Because for instance, if we are using M-defined hashes, we see that in theory we can have some hash collision. So do you know if there is something that we are looking forward to look into that?
So what happens is most devices are going to use some kind of RSA signatures. So it's most of the time it's 2K, so 2048 bits. So which is like it's good enough. So you can just like hard code the public key. On our case, we just erase the public key, and only the person who has the private key can sign a new bootloader, can sign a new firmware, and can like update the firmware. So, but what we need nowadays, we need also hardware protections like TPM, like in smart cards and all those
platform module. Yeah.
Trusted platform. So, just by using software-based solutions, you can always bypass. It's good, but not good enough. So
and on x86 devices, we are very mature right now. So like Microsoft has support for TPM, I think Linux nowadays can do secure boot. So every single part of the boot process is analyzed, hashed, and you can basically trust it. And on embedded devices, there's nothing yet.
Mostly because they're cheap and people don't want to spend money on that.
Yeah. Get your hardware from China. It's really good.
One question, maybe. If not, okay, thanks.